No free lunch theorem explains the difficulty of learning. So what is the definition of no free lunch theorem? So let's read. Let A be any running algorithm for the task of binary classification with respect to the 0-1 rows over domain X. Let N be a training set size such that N is smaller than the cardinality of your domain X, input domain X over 2. Then there exists a distribution D over X which defines on X such that there exists a function f from X to 0 or 1 with a test error equal to 0 with probability of n is 1 over 7 over the choice of your training samples. We have test rows expected test error is greater than or equal to 1 over 8. Okay, so what is the meaning of no free lunch theorem? This is essentially when your training samples is not sufficiently many, it's not enough to cover whole domain. There always exists some special case of sample distribution or your data generation process that make a huge classification error. Here, huge is not such huge. It's greater than 1 over 8. So this is pretty bad because when you want to like 10% of error or 5% of error, basically when your sampling size, your training set size is less than or equal to the cardinality of x over 2, then it is impossible with any algorithm. Okay, this is no free lunch theorem, but you also have to look at the first sentence. There exists a function, there exists a true function f that make a such error. Okay, which means there also exists some function that make very nice test error. If a true function f that make a zero test error has some nice property like a very smooth shape or is very simple shape, and we know the information on f with not enough training sample with less than the cardinality of x over 2 number of samples, we still can guarantee very nice test error. This does not contradict with the free lunch theorem. Because no free lunch theorem, you have to understand this point. In the no free lunch theorem, we are saying there exists a function f that can make such bad behavior, which also means there could exist another function class f that can have very nice test error with some type of hypothesis set. Okay, that also possible, and we will discuss such a nice case, such good case next week in VC dimension theory. The why we have to study no free lunch theorem. In no free lunch theorem, we are saying the difficulty of learning. When we have some small sample size, small training set, then we can provide some counterexample under the condition, under the example, your given learning rule does not work. Okay, for any given learning rule, when the training sample size is not enough to cover whole domain, your training set size is less than half of your training domain, your input domain, then we can always provide some counterexample. With the counterexample, your learning rule does not work. Your learning rule make huge test error. That is the key point of no free lunch theorem. Okay? I want to highlight again, no free lunch theorem does not mean with this x over 2 less than x over 2, the cardinality of x over 2 training sample, we always fail to train. The no free lunch theorem does not mean that. There could some function, there could some true function class f, and if we know some information of the true function, then even if our training set is less than the cardinality of x over 2, we can still train our model with nice test error. Okay. In no free lunch theorem, we are saying there exists a counterexample that can destroy your training rule. Okay, you have to understand the difference between there exists and always. Okay. Anyway, from the no free lunch theorem, we have this statement: we cannot make a universal algorithm. So, what does universal algorithm mean? With any type of ground truth function, with any type of data sampling process, an algorithm can provide very nice test error. Then we say the algorithm is universally good algorithm. But no free lunch theorem tell us for any given training algorithm, we can provide a counterexample that destroy your training algorithm, training rule. So when H in your hypothesis class, the empirical risk minimization has the test error greater than or equal to 1 over 8 with a probability less than or with a probability less than 1 over 7 with this number of samples. Okay, so this comes from our pack learning theorem in the previous example. So why this is holds? Although the no free lunch theorem holds, in no free lunch theorem, whenever n is less than or equal to the cardinality of x over 2, then we can provide some counterexample that have very bad consequence. But from the pack theorem, whenever our sampling budget or the training set size is greater than or equal to this, then we can guarantee the test error greater than or equal to 1 over 8 is less than or equal to 1 over 7. And this can be much smaller than the cardinality of x over 2. So it looks like it contradicts with no free lunch theorem, but the answer is no, because here in the pack learning theorem, we are using the fact that we are restricting the ground truth function f as a member of our hypothesis class. So we have additional information on the ground truth function h. If we have such information, there could a learning rule that can make a very nice performance with less than the cardinality of x over 2. Okay, so that is also very important point.